Okay, how's everybody doing? I wanted to shoot a quick video giving us some introduction, if you will, to chapter 17. This video is going to be focused on what is a titration, right? From a definition standpoint, also from a conceptual and acid-base equilibrium standpoint. So, a titration by definition is when you add a base to an acid to create water and, in most cases, a ionic compound, a soluble ionic compound. Generally speaking, that ionic compound is the conjugate acid and conjugate base of both of your acid and your base interacting with one another, because normally they're going to be charged species. So to give you an example that is not generic, if we were to take HCl and add that to NaOH, we would create water and NaCl. Again, all of these are aqueous except for water, and don't forget that when you're writing them. Okay, now what we should at this point be familiar with and be able to remember is, can we describe each of these as a strong acid, strong base, neutral, weak acid, weak base? Now, HCl is a strong acid. We know that based on knowing our 6 to 7 strong acids. Sodium hydroxide, anything containing hydroxide, is considered a strong base. So we know that. Now, what about water? We know that water can be both, depending on the situation. And if we remember, any conjugate of a strong acid or strong base is in fact neutral. So we are dealing with a neutral species that is created. So this is considered a titration. A titration involves specifically what we call a neutralization reaction. And we should remember that from General Chemistry 1. Okay, so when we talk about chapter 17 and additional aspects, one of the major things that we're going to be discussing is titrations and how to do the calculation. Now, here I gave you an example of strong acid, strong base. There are other examples of titrations that do not involve both strong species. So if we took a look at HF, which is a weak acid, plus sodium hydroxide, we're going to end up with water plus sodium fluoride. Now, still a neutralization reaction, right? Still acid base, but we're dealing with a weak acid now and a strong base. Remember, strong bases dissociate completely. Weak acids dissociate somewhat. But because the hydroxide is in solution, the acid-base chemistry that's occurring is between the H and the OH to create this water. Now, leaving us with sodium fluoride in solution. And if we go back to our General Chemistry 1 understanding, we should be able to understand that unless these are equal amounts of moles, we are going to have one or the other left over, right? We're going to always have one or the other left over. Now, let's talk about the other example, is when we're dealing with a strong acid, let's say nitric acid, plus a weak base, let's say NH3. Now we have NH4 plus nitrate. So in this scenario, we have a strong acid dissociating completely. We should describe this as a strong acid. We have ammonium, which is a weak base, and we see it creating the conjugate acid, which is a weak acid now, and nitrate, which is neutral, right? We should understand that this is neutral. So a weak acid here means that we are adding acidic stuff to the system when we dissociate and react here. So here we should remember that sodium fluoride is in fact basic. How do we know that? Well, because fluoride is the conjugate of a weak acid, so it should act basic in solution. So we have an acid, base, a basic ion is formed here. Here we have an acid base, but an acidic ion is formed here. And more specifically, you can label this as a weak base, to be specific. So each one of these scenarios you're going to have to be able to recognize, because these are three different types of titrations. These are the three different types that we are going to discuss over the course of this class. Strong, strong, weak, strong, and then strong, weak. And I'm going to erase this. I'm going to talk about how we approach each one. So let's talk about the first one, because this is a basic situation that we should have seen before in General Chemistry 1. So in General Chemistry 1, when we talked about acid-base stoichiometry and the stoichiometry of all reactions, not just neutralization, specifically the reaction of neutralization, in this case, is going to be 1-to-1, right? We see that we have a 1-to-1 to 1-to-1 stoichiometric ratio, which means that if we have been given a volume of either of our components, then we should be able to, and the concentration, we should be able to know how much water and sodium chloride we are expected to produce. So that's what brings us to this concept of analyte and titrant, right? Analyte and titrant. The analyte is what you are analyzing. The titrant is what you are putting in. And we're going to get to that on a systematic level here in a second. So we're dealing with stoichiometry. If I told you that we put 100 milliliters of 0.1 molar HCl and we added that to 50 milliliters of 0.1 molar NaOH, I have given you enough information for you to determine the number of moles, right? And then from there we can determine limiting reagent. We can then determine what is going to be left over, excess, etc. So the number of moles in each of these, the number of moles here is 0.01 moles of HCl. Remember, we got 0.1 times 0.1, and here it's going to be 0.005 moles of sodium hydroxide. Now, what we should be familiar with at this point is that acid and hydroxide form water and the ions, and those ions are in fact neutral. So from a stoichiometric standpoint, if we take 0.01 moles of HCl and we show that there's 1 mole of NaOH for every 1 mole of NaOH for every 1 mole of HCl, then we need 0.01 moles of NaOH to use up our HCl completely. And we do not have that. We do not have that. Therefore, this is our excess, right? HCl is in excess, which means our limiting reagent is in fact sodium hydroxide, and we should use that to calculate. So 0.005 moles of NaOH, and for every 1 mole of NaOH, we are using up 1 mole of HCl, which means that we're using up 0.005 moles of HCl used. Again, this is basic stoichiometry from General Chemistry 1. Now, how do we apply it to acid-base equilibrium is what we're going to learn today. So, if we've used up 0.005 moles and we started with 0.0 moles, the number of moles left of HCl remaining is equal to 0.005. moles. Hopefully you see, and I did some basic calculations to show us that, but hopefully you see that this was a simple, straightforward calculation. We used up half. Now, the majority of titration problems involve your ability to determine the pH of this system after we have added in the acid or the base. So if we know that we have 0.005 moles of HCl, then we should know that the concentration of HCl is also equal to the concentration of H3O plus. Why is this? This is because HCl and H3O plus are equal to one another whenever we're dealing with a strong acid. So this is equal to 0.005 moles all over the total volume. The total volume. So V total now in our solution that we have formed is equal to 150 milliliters or 0.15 liters. So now we're dealing with a situation where we are dealing with a higher volume than we started with. So we're dealing with 0.15 liters, and therefore we're dealing with a concentration here that is equal to 0.005 divided by 0.15. Let me grab the calculator. And we have 0.033333. 0.033 molar. Now from here, we should be able to determine pH by taking the negative log of 0.033, and we should see that the pH is equal to 1.48. And that is what we should expect. We have used up all of our base. It is our limiting reagent. And you'll see me write that as LR. We have leftover acid, which we know is dissociating completely because it's a strong acid. Therefore, we can equate the concentration and relate that to pH. So this is an example of a titration before what we call the equivalence point for a strong acid, strong base. So this is before what we call equivalence, because we have not used up all of either of our acid or our base. Okay. All right, now let's talk about a situation where we might be at equivalence. Okay. So let's say that we had 100 milliliters and 0.1 molar HCl and 100 milliliters and 0.1 molar NaOH. Now, without doing very much stoichiometry, you should be able to recognize that the number of moles of each in each of our solutions that we're adding together, those number of moles are the exact same. And since those number of moles are the same, we have a 1-to-1 stoichiometric ratio, we expect for there to be the same number of moles of sodium chloride and water formed, and we have used up all acids and bases. Now, this is a neutralization reaction that is going to completion because we have used up all. And if we have used up all acids and bases and we're only left with water and neutral salts, we should expect the pH to be approximately 7. Right? The pH is approximately 7. But this is a function of strong acids and strong bases in a titration. This is not the case always. You just have to remember that pH is equal to 7 when you're dealing with strong acid, strong base. This occurs what we call at equivalence. So at equivalence, meaning the number of moles of acid and base are equal, we should have pH approximately 7 when we're dealing with strong acid, strong base. Doesn't matter which strong acid or strong base, as long as they are considered such. So we talked about before equivalence, we talked about at equivalence. Now let's talk about after equivalence. So after equivalence would be if we were to add more sodium hydroxide. So let's say that we had 100 milliliters of 0.1 molar HCl and we had 200 milliliters of 0.1 molar NaOH. Now, sodium hydroxide is not the limiting reagent. It is now the excess, and it is the excess as a function of 0.02 moles of NaOH, and here we have 0.01 moles of HCl, which means that leftover, and I'm not going to go through the stoichiometry. At this point, you should be comfortable with dimensional analysis and the stoichiometry side, but what we are left with is 0.01 moles of NaOH. That is what remained, right? Now, our pH of this solution, we can call this after equivalence, is a function of a strong base dissociating completely in a solution of water and a neutral salt. So now we have 1 mole left over the total volume, which in this case is 0.3 liters, and therefore we're dealing with 0.01 divided by 0.3, so 0.033333. Okay, and now we are dealing with POH, which is equal to negative log of 0.033, and POH is equal to then 1.48. Therefore, pH is equal to 12.52. Now, we have a basic solution, which is what we expect because we have a leftover strong base in a solution. So, after equivalence in this case, we have a basic solution. Before equivalence, we have an acidic solution. And at equivalence, we are neutral. So which one is the analyte and the titrant in this scenario? So whatever we are adding in, whichever one is going to be the limiting reagent before equivalence is the titrant. So our titrant in this scenario is sodium hydroxide. We are using sodium hydroxide. We did not have enough at first. So we have a before equivalence. At equivalence, we had the exact same amount. And after equivalence, we had excess of our titrant. Therefore, what were we analyzing? What were we putting our solution into was HCl. So our analyte in this situation is HCl. Okay? Now, what does that look like? So if we were to track or graph, you know me, I'm always wanting to look at graphing something. If we were to graph the pH as a function of milliliters of titrant, if we remember, our first milliliters of titrant was 50, our second one was 100, our next one was 200, right? So we got 50, 100, 200. Okay? And if we remember our pH at first was acidic. It was about 1.48. So if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It was about 1.5 at 50 milliliters. And then at the equivalence point, we said that it was 7. So we got 1, 2, 3, 4, 5, 6, 7, 14. At 7, it was here. And then at 200, we see that it's 12.52. So 11, 12, 13, 14. So 12.52, roughly about here. So if we looked at the points on the titration curve, we see that we have 3 points. Now, what does a strong acid, strong base titration curve look like? Well, if we measure the pH using a pH meter throughout the entire titration, you would see that the pH would start, and then we would have a sharp increase through 7, and then we would have a curve that looks something like this, right? So the titration curve, which is what I wanted to talk about for each of these at the end, for a strong acid, strong base titration, involves a very steep increase or decrease at equivalence. It is very steep, and the reason for that has to do with it being strong and strong. We're going to talk about the buffering in class. Okay, so this is strong, strong. One scenario, notice that in this case I use the titrant as the base and the analyte as the acid. Now, what does the reverse of this look like? So the reverse of this, if we had a basic analyte and a acidic titrant, we would be dealing with a curve that goes in the opposite direction, but very similarly shaped, right? Very similarly shaped. And you'll see some examples of this in your worksheets and homework. Okay, so this is before and after for strong acid, strong base titration. We're going to do that in the laboratory. Now, let's take a look at another example. Now, if we take a look at the example, and I'm going to erase the graph too, because we're going to make a new graph. Now, if we want to take a look at an example of a weak acid, strong base, so we can take a look at the example that I wrote up here before. Let's use, yeah, that's fine. We'll go HF titrated with potassium hydroxide to create water plus potassium fluoride. Also 1-to-1-to-1-to-1 stoichiometric relationship. But now we're dealing with a weak base and, a weak acid, and we have created a basic anion. Why is this basic? Remember that F minus in the presence of water is in equilibrium with HF and OH minus. So both of these are in equilibrium. Just because we are creating or neutralizing a certain amount of the HF does not mean that we are dealing with a reaction that is not still in equilibrium once it is neutralized. So what we have here is a situation where as we create F minus is also trying to do this reaction. So we have to take that into consideration when we're dealing with the stoichiometry of a titration using a weak acid. So what does that mean? That means that the number of moles that we add, and I'm going to also use a very simple example here, 100 milliliters of 0.1 molar HF, and let's say we are using a titrant of a base, and let's say we're going to go 50 milliliters of 0.1 molar KOH. Okay, now from our last example, we know that we're going to be left with 0.0 0.05 moles of HF. I'm kind of skipping through the math here. You can pause the video and do the math and confirm that. But KOH is our limiting reagent. HF is in excess, our weak acid, and we're going to be left with 0.005 moles of HF. Now, what does that also mean? If we know and remember our stoichiometric rules, we're also going to be creating 0.005 moles of F minus. If F minus and HF are both interacting with water to do acid and base reactions, we have to consider both of them when we're dealing with the idea of pH, right? We're dealing with the idea of pH. And therefore, to know the amount of H3O plus that is in solution, right? And the amount of OH minus that is in solution, as a function of each of these, we have to take into consideration the reaction of HF with water. So this is the titration reaction. But after we have used up the base, we are no longer dealing with a titration because we don't have any base. So now we have to take into consideration the reaction of HF with water to create hydronium plus F minus. Now, if we remember our equilibrium rules that we just learned in the last chapter, we now have an ice table scenario. And as long as we know the Ka for HF, we can determine the hydronium concentration as a function of Ka using the ice table, because now we know the number of moles of each of these. More importantly, we need to know the concentration, so we need to divide that by 0.15 molar and divide this by 0.15 liters, excuse me. And that gives us molar concentrations of each of these. So 0.005 divided by 0.15 and 0.005 divided by 0.15. So we have a 0.033 molar and 0.033 molar of each of these. So that is our initial concentration, because that is what is left over, 0.033. Remember, water is unnecessary. We're going to assume this is the starting of the reaction. So we have 0, and now we have a situation where we have a minus x, plus x minus x, 0.033 minus x, 0.033 plus x. Now, if we remember how to form our Ka expression, Ka is equal to H3O plus F minus all over HF. So again, to recap right here, this is where a lot of people get confused. The first thing that we did was a titration, where we know we have a 1-to-1 ratio of acid to base, leaving us with a neutralized water, but also giving us potassium fluoride and the fluoride ion. But once that is done, we are now dealing with another acid-base equilibrium reaction, but that is between HF and water, because HF and water and F minus are all going to create an equilibrium, forming some H3O plus, because we have acid left over. And that is a function of these two values. So what we're left with is x 0.033 plus x and 0.033 minus x. If we look it up and determine the Ka for HF, and I'm going to look that up real quick. HF has a small Ka, which means that it is a very weak acid. If it is in fact a weak acid, remember, we can drop the X. And that value is 6.6 times 10 to the negative 4. So if we have 6.6 times 10 to the negative 4 is equal to x all over 0.5 0.033 over 0.033, right? We have X is equal to 6.64, which means that hydronium ion concentration is equal to X in this case, and therefore pH is equal to negative log of 6.6 times 10 to the negative 4. And we should have a slightly acidic pH, 3.18. So we're dealing with a pH equal to 3.18. So even though we are at the titration, we are still before equivalence, we are dealing with an acidic solution still because we have leftover acid. We had to do the stoichiometry to find out how much we had left, how much conjugate we formed, and then we had to use the ice table to then plug it back into our Ka. So if we know Ka, we know these amounts, we have to be able to do this process to give us the pH of the resulting solution, which is a function of the acid-base equilibrium.